This is work, I'm Dave Thompson. It's nice and bright in here. This is work, so you can see me, done with Ying Li, who's a postdoc at Colorado State University. This is also kind of a series of papers with Graham Stevens on some of them, Sandrine Bony's on some of the papers. And the big picture of the work that Ying and I are doing is trying to understand the two-way interactions between clouds and large-scale dynamics, primarily in the exotropics. And we've been using models to do so, and also some a fair bit of observations, for example, CloudSat. So what I'd like to do in the half an hour I have is, I'm just joking, in the first 7.5 minutes, I'm going to go through some results that, most of this is Ying's work, that I'm just giving you a flavor for that document the impact of large-scale variability on clouds, and this is mainly observational work, and then I'll highlight some of her work showing how clouds, or the cloud radiative effects in turn, can affect the large-scale atmospheric circulation. And so the way it is, of course, with 12 minutes and 51 seconds is that it's just going to be a taste of what we're looking at. Okay, so this is the primary two sets of results. The first part here, as I mentioned, is the influence of large-scale variability on clouds, and then vice versa. So if this was a dynamics session, I wouldn't even show the next figure, but I'm going to show it because I realize there are some in the audience who are not necessarily work with large-scale dynamics every day. But what I'm going to do is I'm going to highlight the influence on clouds of the two of the patterns that are most important in the large-scale Southern Hemisphere circulation. So this is the structure of the southern annular mode. It's been shown for decades in different papers, but I just want to show it so you know what it looks like. So when I show the clouds, you have something to refer to. And what it describes, this is the dominant pattern of variations in the wind about the climatology. And you have westerly winds in the contours here, and easterly winds in the dashed contours here. And what that's telling you, this dipole in the winds, is that the dominant form of variability in the southern hemisphere is north-south meanders of the jet in the southern hemisphere circulation. So part of our work, and other people have done this, Paulo Ceppi and Kevin Grice, as you'll see later, is trying to understand how do those north-south variations in the jet project onto clouds. So some of the, this is on the left, I'm highlighting some work from Kevin Grice and Lorenzo Polvani, and then some recent results from Ying on the right. So this is showing, these are regressions onto the SAM, or different indices of this southern annular mode. So the regressions onto a time series that describes the variations in the jet about its mean axis. And the big picture here is that you get, if you squint your eyes, and generally you get a dipole between lower and upper levels. And in this case, you have, say, less clouds in lower levels and more clouds at upper levels. And this is from an ISCIP product. On the right is results from CloudSat. So this is a regression that Ying's done. And again, it confirms, I think, largely what you see here, but you get this nice vertical dipole structure. So it turns out, of course, that this pattern then matters for long-wave radiative effects, but less so for short-wave because of that vertical dipole. And as Kevin will highlight later in this session, that models get widely different. Their ability to reproduce this varies greatly from one model to the next, and that matters for a variety of reasons. So that's one pattern of variability in the circulation and what it looks like in clouds, and that's part of our work, is looking at this. Another pattern of variability, which is maybe more interesting from a cloud perspective, is, and this is a whole other topic really for another talk, but this is the leading pattern of variability in eddy kinetic energy in the southern hemisphere, and the eddy kinetic energy is shown in the contours here. And without looking at the figure, you can just sort of think, well, what this pattern describes and what it tells you is that the dominant pattern of variability in eddy kinetic energy in the southern hemisphere is a pulsation of eddy kinetic energy, a monopole. And that means that wave amplitudes, baroclinic waves, go through periods of either having larger amplitude than normal or smaller amplitude than normal, right? And that particular pattern of variation explains a large fraction of what all storminess does in the southern hemisphere. So you have periods when you have larger wave amplitudes and smaller wave amplitudes. It's not this north-south dipole in wave amplitudes. And the projection of that onto clouds can also be found through, say, correlations or regression. And it gives you this monopole in upper tropospheric clouds. This is shown from the CloudSat data, a regression on a time series of that pattern. This would be similar if you just took eddy kinetic energy in the southern hemisphere atmosphere, averaged it over the whole southern hemisphere, regressed onto that, this is what you get. And it just makes sense. When you have larger storm amplitudes, you have more clouds. And this is just the analogous plot from Error Interim to show that it does a pretty good job. And it's not trivial to make these plots with CloudSat. As you can imagine from those swaths, right, that Graham showed in the previous talk, taking those and creating this gridded product was something special. Anyway, one reason that this pattern in eddy kinetic energy is interesting is its time variation. So if you were to look at the power spectrum of practically any field in the exotropics, say temperature or the zonal wind, the spectra are red, right, first, or white after a certain time scale. But the power spectrum of this baroclinic annular structure, of this, it's called baroclinic because it's baroclinic, I guess, and it's called annular because it's ring-like. But the power spectrum of this is not red. It's interesting, and this, again, is a topic for a different talk, but it's relevant to this one. So this is the spectrum of that baroclinic annular mode. You could think of this as, this is the power spectrum of eddy kinetic energy or wave amplitudes in the Southern Hemisphere, average over the entire Southern Hemisphere, and it's not red at all, right? This is lower frequencies on the left, high frequencies on the right, and this is coming out of work that I did with Libby Barnes over this last year. The point is that eddy kinetic energy in the Southern Hemisphere pulsates on a 20 to 30 day time scale. This is a great peak, right? This is the kind of figure I've joked about before that I made at 5 to 5 before I had to go home for the day. And then you're like, oh, you just want to follow up on it, and you go home and you're reading some book to your kid in bed, and you're not really reading the book, you're thinking about this power spectrum. But anyway, you know how that goes, because you can only read Bob on the Farm so many times. So anyway, what's interesting, so you get these variations in eddy kinetic energy, and they pulsate in this 20 to 30 day time scale, averaged over the entire Southern Hemisphere. And it makes sense that variations in eddy kinetic energy project onto, say, clouds and onto precipitation and different parameters. And so one question we had is, do you see that periodicity and other variables related to this section? So the red line here, the left, is showing the power spectrum of precipitation averaged over the entire Southern Hemisphere. This is, again, cycles per day. And what's interesting, if you just simply take precipitation averaged over the Southern Hemisphere from two different products here, one's remotely sensed and one's from the air interim output, then they both show a peak around that time scale, which makes it's physically consistent, and it's cool, right? I mean, the idea that Southern Hemisphere precipitation has this pulsation to it is interesting. So this is, again, I think, one cool impact of large-scale dynamics on, say, precipitation. But on the right here is the impact on cloud radiative effects. So this is the top of atmosphere, long-wave cloud radiative effects from the AIRS instrument, and it also has this, what appears to be a peak in the spectrum. And again, it's very robust, right? You can test this against a red noise spectrum. I don't have the lines of significance here, but you can tell it's dominating the spectrum in that frequency band. So long-wave cloud radiative effects have this nice pulsation in the Southern Hemisphere in 20 to 30 days, and why that matters we haven't sorted out yet, but I suspect it must matter from some climate perspective. And I'll point out that this peak in the spectrum isn't particularly, I'm not sure it's going to show up at individual. I don't see precipitation in Christchurch having this regular rhythm to it, is the point, right? Because you've got a lot of the variability, but averaged over a broad region, you see it. And the work with Libby, and it's on my website, we go through the physical mechanisms for this, and there's some plausible mechanisms, and I won't go into those. So those are all results of large-scale variability influencing clouds, say, and precipitation over the Southern Ocean. The other stuff that I wanted to at least touch on here is some work that we've been doing. This is mainly with Sandrine Bony on the influence of clouds on large-scale climate variability, and I'll highlight some results. Oh, I guess I don't really need, oh, there it goes. From the Cookie experiment. So this is Bjorn Stevens and Sandrine Bony have a nice white paper on the set of experiments. And the big picture here, I'm switching from observations to numerical results, and there's two types of experiments. One type of experiment, right, you have the all cloud radiative effects are on in the model, and in the other experiment, all cloud radiative effects are turned off. And the SSTs are fixed, so there's not going to be much change in short-wave radiative forcing, but you'll get large changes in the long-wave radiative forcing. So by examining, a lot of people may have heard of these runs, by examining the difference between these runs, you're then isolating the importance of cloud radiative effects for climate, and I'll focus on some results in the Southern Hemisphere. The runs are analogous to Slingo and Slingo 88, for example, right? These are, but following that same intellectual thread. So, just to highlight some cool results, I think, from this. This is the cloud radiative effects in the clouds on experiment. So this is the total, say, heating due to cloud radiative effects and the cooling up here where you're radiating to space, and then the cooling down here in the boundary. This is all in K per day. So effectively, by turning off the cloud radiative effects in the model, you're imposing this heating onto the model. And this, of course, is dominated by the long wave component because sea surface temperatures are fixed, right? So what I'll do is just highlight the differences in the mean climate of the model between when clouds are doing their radiative thing and when they're not. So the first figure shows the differences in long-term mean temperature in the atmosphere and tropopause height between clouds on minus clouds off. So this is showing you the temperature changes that are due to the cloud radiative effects, and they somewhat mirror the pattern of radiative effects, but not perfectly, and that suggests that something dynamical is going on. And what's important for the Southern Hemisphere here, and I think this is mainly coming from the tropical clouds, but you have this increase in the north-south temperature gradient here, and you'll also have a decrease in the static stability here. And so what you're doing is you're destabilizing the extratropical upper troposphere in the Southern Hemisphere by including cloud radiative effects. And that's going to do two things. By increasing the baroclinicity in the atmosphere up there, you would expect wave amplitudes to be larger, simply because there's more potential energy for, when I say waves, I mean baroclinic waves, for storms to grow. And you might also expect the momentum fluxes to change in the upper atmosphere because they go along with wave amplitudes. You know, it went from green to yellow to green. Is that, I'm sorry, okay. I just keep going. Anyway, so this is the influence of cloud ray effects then on eddy kinetic energy. And red means there's more eddy kinetic energy in the atmosphere when you have cloud radiative effects on. And the key thing here is there's a 30% increase in atmospheric eddy kinetic energy when you add cloud radiative effects to the model, right? So if your cloud radiative effects are off in some way, then the development of storms in the extratropics, the extratropical southern hemisphere over the Southern Ocean is going to be widely different, which I think is interesting. This is the changes in the zonal mean zonal wind between the clouds on and clouds off experiments. The stuff in the tropics is interesting. I think that's because of changes in the amplitude of the equatorial planetary waves, but it's the Southern Hemisphere that we're focused on here. And the main thing is this red line here with the little dots is showing a significant increase in the wind speeds over the Southern Ocean. And this is coming from the momentum fluxes aloft, and again, as Paul Sheppy has pointed out, in association with the shortwave effects, but the long-wave effects of clouds, really matter in terms of getting the Southern Hemisphere circulation right. And I think my last scientific figure on this is the influence of cloud radiative effects on precipitation, and I'll just focus on the Southern Hemisphere, but by including cloud radiative effects globally, you increase precipitation here and decrease it here. And I'll point out that these changes in precipitation, of course, are coming from changes in vertical motion, and the changes in vertical motion are coming from the momentum fluxes by storms aloft, which is coming from the baroclinicity. So the big picture being, by getting the right cloud radiative effects or having them in the model, it changes the baroclinicity so much that it changes the vertical motion substantially in the extratropics, and that's why precipitation is changing. So we couldn't understand the problem unless you were really thinking of both dynamics and clouds there. So the key results so far in the work are, one, that patterns of large-scale climate variability, they have this robust signature of clouds in the Southern Ocean. I think the work on this has just increased dramatically over the last few years, right? Because of the availability of data sets such as CloudSat that allow you to do that, to see that. I think one cool scientific result that we're following up on is this idea that the long-wave radiative forcing in the Southern Hemisphere has this robust peak to it, and whether that matters for the general circulation is something we're exploring. Cloud radiative effects play a central role in setting the amplitude of the Southern Hemisphere extratropical storms, and perhaps this is not surprising, but it's nice to be able to tease that out and see that that's the case. And in general, there's strong evidence of two-way feedbacks, just like I said in my title, between clouds and dynamics in the Southern Hemisphere ocean region. Thanks for your time. Oh yeah, Jennifer?
Given that many climate models underrepresent the cloud radiative effects over the Southern Ocean, given these results, what do you think that implies for their dynamics and deficiencies in their dynamics?
You mean the dynamics in the atmosphere? Well, one thing The results we're looking at are the response to long-wave cloud radiative effects, and they clearly matter for the dynamics. I mean, the Southern Hemisphere circulation is going to be out of whack if the long-wave radiative effects due to clouds are out of whack. But Paulo Ceppi's work has highlighted also the role of short-wave radiative effects, right? And they mess up the circulation. And of course, if your circulation's wrong in the mean, it's going to be messed up in the trends, as other people have noted. And I'm kind of dancing around the answer to your question. I guess I would say it matters.
Thank you.
Yeah, thanks.